Let's take a look at this effect of the acceleration due to gravity. So here we have the situation of a person standing in an elevator. This person, for some reason, has a scale with them. We're not really sure why, but they do. Maybe it was being moved from floor to floor and he just took the advantage to stand on it in the elevator. But this scale is showing his weight. It's showing his weight, however, as an apparent weight in terms of pounds. Remember, when we do a calculation in terms of weight, we're usually looking for something in terms of a force, i.e. the acceleration due to gravity 9.8 multiplied by your mass. So this is a little unusual in terms of a physics description, but here we're saying that this scale will show the force that this man is exerting on this scale. He will also be subject to motion due to the fact that he's in an elevator. Now, we're going to say, for the purpose of this experiment, that you can see he's in the elevator alone with just a scale. As such, he doesn't have a box of Twinkies or anything else that he can put in his pockets, so his mass is staying constant. So keeping his mass constant, we have several examples here. First of all, what should happen as the elevator moves at a constant velocity? Well, as the elevator moves at a constant velocity, the answer here that you should be thinking is it'll be the same case as a stationary reading. So his reading in the stationary elevator is 140 pounds. Remember, force is equal to mass times acceleration, and this particular scale in this scenario is showing the force he's exerting on the scale. So moving at constant velocity, our acceleration is 0, and so he will end up showing the same weight whether he is moving or standing still. Now, what happens if the elevator accelerates upwards? Remember, in this case, g of negative 9.8 is acting downwards on this entire system. Well, for the case of an accelerating elevator upwards, he'll see his apparent weight shift from 140, because he's working against gravity here, it'll jump to 160 pounds. Likewise, if he accelerates downwards, we should see a corresponding reduction in his apparent weight. So accelerating upwards, we saw a jump from 140 to 160. Accelerating downwards at the same rate, we'll see a reduction in the apparent weight on this scale of the equivalent 20 pounds, giving 120 pounds. So accelerate downwards with gravity and you should see a reduction in the overall weight that's shown on the scale, due to the forces being diminished on him, given his direction of acceleration. If he accelerates upwards, you should see an increase in his apparent weight. Now for the final question, what happens if this elevator goes into free fall, and in this particular simulation you'll see that the cable snaps and this man falls to his doom. In a real situation, by the way, elevators would have brakes that would kick in this particular scenario and hold you still until a rescue came. As you can see, it's a very crude elevator shaft just made out of bricks. But getting back on point, if the elevator goes into free fall and he falls for long enough, you should see a situation where in free fall he will be weightless. So the scale would read 0 pounds. So, just in review, remember the mass that you actually experience, your mass will be the quantity of material that you are made up of, or the object you are studying is made of. Weight is a force acting on that mass, and objects are weightless when in a state of free fall. So, even if you are in orbit, gravity is still acting in space. Astronauts are not actually weightless in the true sense of the word. The gravity even in a relatively high Earth orbit is still approximately 9.8 meters per second. What's actually happening is you are orbiting the Earth in what's referred to as a constant potential. And weightlessness is an effect of constant free fall, constantly falling but missing the Earth, essentially. And here is that effect. As people train for the rigors of spaceflight, it is good to actually simulate zero gravity without actually spending all of the money to put people into orbit. And as such, one way of doing this is to use NASA's KC-135, or the affectionately known Vomit Comet, to simulate zero-G conditions. The way this is done is this aircraft will accelerate in a parabolic trajectory. That is, it will fly upwards, and we've looked at parabolas in two-dimensional motion, level out, and then dive towards the Earth. And as we saw in our last slide, if you make one of these dives towards the Earth, you should end up with a situation where the effect inside the aircraft is to put everybody into free fall. You will of course have to pull up relatively quickly so the aircraft doesn't hit the ground. So in these controlled dives you can actually generate several seconds of zero gravity inside the aircraft. On the upwards and downwards pulling in and out of this particular maneuver, you actually generate 1.8 G more than Earth's gravity. But for a few seconds you can experience 0 G while you are in free fall. Now, this is particularly useful for training astronauts for the rigors of space, filming movies like Apollo 13, or for tourists who have $6,000 a trip to go up and eat M&Ms in a 0 G environment, and they let you keep the suit. So, we previously saw Newton's law of gravitation, the statement that every particle in the universe attracts every other particle of force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them, or F is equal to gm1 m2 over r squared, where Newton's discovery was the large G, the universal gravitational constant, whose units have gone off of the slide. Remember, if you are using this particular equation, the r in the r squared on the bottom of that equation tells you the separation of the centers of mass. Now, if you are talking about the center of mass of the Earth to the center of mass of, say, yourself or even a spacecraft in orbit, then the radius of the spacecraft or yourself may be on the order of half a meter, maybe 10 meters, but that's extremely small compared to the radius of the Earth. Usually, adding on the correction for the radius to the center of yourself or the center of a spacecraft is a small addition that we usually don't bother with when we're looking at the radius of the Earth overall. But if you're looking at, say, the gravitational attraction between the Moon and the Earth, or the Sun and the Earth, then the radius of the body makes a big difference. Newton's gravitational equation, gmm over r squared, goes from the center of mass to the center of mass. If we were to calculate the distance between these objects and were given the surface separation from the surface of, say, this object to this object, we would then have to add on the radius of these objects. Always check every question that you do. Is the separation from the surface to the surface? Do you have to add on the radius of the objects? Or are you looking at r being a separation of centers of mass? So, Newton's law of gravitation basically tells you that all objects with mass feel an attraction between them. There's a gravitational attraction between you and every piece of matter in the room, but it's very, very small because it's based on the proportion of masses. The Earth's mass is enormous, and so you feel a much greater attraction towards the Earth than the Earth does to you. But the Earth is still attracted to you. So if you jump up in the air, the Earth wants to move towards you. It won't because of its overwhelming mass. So the larger the mass, the stronger the pull. Earth will always win against you. And of course, this was the inverse square law. And the statement here is that for every Earth radius we go, force of gravity will fall off by essentially that radius squared. So 623 over 1, 623, go to 2 Earth radii, 155.8, 3 Earth radii, we're looking at essentially a factor of 4 falling off here when they're each time, 69, 39. And there's what this graph would look like. So let's take a look at Newton's actual laws of motion. We looked at Newton's gravitational law. Now let's compare this to the laws of motion. The first law, of course, made the statement that an object at constant velocity continues to move at constant velocity unless a net force acts to change its speed or direction. This means when something's moving, a velocity must act against it, or an acceleration must act against it to bring it back to zero, or you have to actually apply a force to something to start it moving in the first place. So a relatively common sense law that we have to take into account. So it means that stationary objects won't move unless you make them move. And once it's moving, another force has to act on it in order to stop it. So in this particular case, we have an 8 ball, and we're going to roll it along a solid surface, a flat surface, giving it an initial force. Eventually, surface friction, that we're going to talk about shortly here, and air resistance, which is a relatively small effect, will bring the ball to a stop. So a rolling ball will eventually stop moving due to these effects. That's a basic statement of Newton's first law. If we take the case of an astronaut, though, moving in the vacuum of space, and we say space is a vacuum, but there's still 2-3 particles per cubic meter, even in the best vacuum of space, those will provide very, very little friction and very little resistance if he's to hit 2 or 3 molecules per cubic meter. So, essentially, if an astronaut fires his rockets, and this particular backpack is referred to as a manned maneuvering unit, a way of flying around in space untethered by a spacecraft. So if he fires the MMU here, he will just keep on going and going and going. If he wishes to stop himself, he would have to provide an equal and opposite thrust in order to come to a complete stop. If you want to see this not working, take a look at the movie Mission to Mars. In this particular movie, which is completely unrealistic and completely wrong even in the way it treats Mars, the occupants of a stricken spacecraft decide to escape and go into Mars orbit by themselves. Now, we're not really bothered about the story here, as thin as it is. What we're really concerned with is the fact that these people fire their backpacks so that they can thrust themselves along. When they switch off their backpacks, they stop. So, if you want to see some bad physics, I'd seriously suggest getting a copy of Mission to Mars. It's quite honestly awful. So, after movies that violate Newton's laws, let's look at Newton's actual laws. So, Newton's second law, as we've already briefly discussed, is F equals ma. The only one of the three that has a formula. Force equals mass times acceleration, and one of our guiding formula from here on in. Of course, acceleration features in this formula, and as such that means that you often have to engage with the equations of motion that we've seen in previous sections to determine A and then calculate F. So in terms of F equals ma, if you were to throw a ball, as this person is accelerating the ball, he's providing a force to it. As he lets go of the ball, he's no longer accelerating it, and the ball will move with some constant x velocity, and its path will only be modified by gravity pulling it to the earth and air resistance as it moves through space. Essentially, the two-dimensional motion that we discussed in our previous section. And finally, Newton's third law, often misquoted in commercials and philosophical discussion, but as far as physics goes, for every action there is always an equal and opposite reaction. And this dictates a lot of everyday and more complex things, and should be considered every time you draw a diagram of a physical system. We're going to move into drawing a lot of what are referred to as free body diagrams, which are diagrams that tell you how your physical system is behaving in terms of forces. So here we have Newton sitting upon the earth. In this particular case, the earth is going to attract Newton, and it's going to attract him with a force that's essentially negative ma, because it's downwards, which will give us a force of negative mg. If there's a force of mg downwards on Newton, this means there has to be a corresponding upwards force of F equals positive mg. This force is referred to as a normal force. This means that the force that's exerted on Newton by the earth is also exerted upwards by Newton in reaction to this force. So, in total, if we're to look at the forces in the y direction here, we would say negative mg down, positive mg up. This will equilibrate his forces, giving him a force of 0, meaning he's not falling down through the earth, and he's not accelerating upwards or moving anywhere. So here his forces equilibrate. And this is going to be important as we move on and look at such things as normal forces. This is the normal force, as it's referred to, the opposition to gravity, the equal and opposite force that's generated by gravity basically providing a force down upon him. And there are effects such as friction where this will factor in. Newton's third law also dictates how rockets behave and the fact that they fly at all. If you take something like a rocket, it's actually propelled by a force that's equal and opposite to the force with which the gas is expelled from the back of the rocket. So, molecular gases are actually forced from the back of this rocket. We combust material in this rocket and force gas particles out the back of it as quickly as we possibly can, giving them an acceleration. That same acceleration will be experienced by the rocket. The rocket is, as you can surmise, usually a very large, heavy piece of equipment. This means accelerating thousands or millions and millions of gas particles out of the back of this rocket per second in order to provide sufficient force for this rocket to fly. There's common misconceptions that when it comes to rocket flight, with people believing that it's the gases coming out of the back that are physically pushing the rocket up. I realize how it could look that way, but that's not what's really going on. It's the equal and opposite reaction of the rocket to the force of expelled gas that forces it to fly. Now, some people have even commented that maybe it was the gases coming out of the rocket pushing against the gases of the Earth. That idea is completely wrong, considering that rockets operate in space, and that's one of our main uses for them. Remember, in everything that we do, that, as we said, mass 2 and mass 1 here, one could be bigger than the other, but they will always fall at the same rate. These are things to keep in mind as we move forward. So remember, mass is the amount of matter in our object, Weight is the force that's acting on that object. I will try to give weights in terms of F, a force, being equal to mg. Often the book will give weights in terms of pounds or kilograms. Please be careful with these. Sometimes this can be a little confusing in terms of the apparent weight. I try to stay in forces, but other sources may not. So, we talked about the fact that the ball in this particular scenario, it doesn't matter if m2 is greater than m1, the two will hit the ground at the same time. And we've laboured on that point several times. But why is this the case? Well, we had F is equal to gmm over r squared. We also have a situation now where F is equal to ma. These are not different types or flavours of force. These are actually the same thing. So, using Newton's second law, we can say F is equal to gmm over r squared is equal to ma. As such, we end up with m on both sides of this equation. If this cancels out, we'll be left with F is equal to gm earth over r squared earth. So this means that if we are dropping a ball towards the surface of the Earth, then the mass of that ball doesn't matter, and all that really factors in here is the mass of the Earth, and of course it would be at some altitude above the Earth, but adding a few meters on compared to the radius of the Earth, of course, would be irrelevant. So our force becomes gm over r squared, which gives us the acceleration of the ball. And this is why you often see accelerations quoted as 9.8 meters per second for gravity, and we don't see things quoted so much in terms of force, because the acceleration can be applied to any value of mass if you know what the acceleration is on a particular planet. And so the mass of an object, a ball in this case, is irrelevant. So let's look at some particle dynamics. Let's look at actual examples and solve some problems through. So, by single particle dynamics, what we're really talking about is the relationship between force and the rate of change of momentum. Remember, momentum is P equals mv, and force is equal to F equals ma. If we change the velocity in that equation while holding the mass constant, then we'll have m delta v by delta t, or ma as it would be, giving us a force back. So, in a case of a few definitions, we can see that Newtonian notation that I talked about previously. If we have velocity, what we have in terms of a velocity function is the position function differentiated, or the first differential of the position being dr by dt, or r dot. We can have an acceleration of the particle, essentially being the second derivative of the position or the first derivative of the velocity. So often, especially when dealing with collisions and dealing with subatomic particle dynamics, you often see a momentum quoted or a momentum function. Usually keeping the mass constant, you can differentiate a momentum function, or you can integrate a momentum function in order to get your force. And so this kind of notation is often common in more advanced physics. So force is the first differential of P, the momentum, or mv gives us mr double dot. So that's the basic equation you need in terms of Newtonian dynamics. F equals ma. Now let's think about a few of Newton's laws and their real effect. The first being a case of an equal and opposite reaction. In this example, you are an astronaut and you have forgotten to put any fuel into your MMU backpack here, and you are floating away from the spacecraft. Just gently moving away from it. You find yourself in trouble, and all you have with you is a toolkit. The question here is, how do you get back to your spacecraft? Well, if you have your toolkit with you, that means you have something that has mass. And if you want to get back to the spacecraft over here, you can use the principle of an equal and opposite reaction. So, by taking a wrench from your toolkit, you could throw that wrench in the opposite direction, a direction opposite to the direction of motion that you really want. So, throwing that wrench, which, even though this is cartoonishly large, so it appears on your screen, will be a much lower mass than the astronaut. If you throw it at a high enough velocity, you should feel a momentum, an equal and opposite reaction, to send you back in the opposite direction and return to your spacecraft. Now, we've just looked at a basic problem here of equal and opposite reactions, but whenever you are solving a mechanics problem of this type, you should really follow the following steps. The first one is sketch the problem. I'm not a particularly great artist, and all I need really is a sketch showing the arrows of the forces involved, the vectors that we need to analyze the situation. Those vectors, they will then lead you into the signs that you will use in your equations. Are two forces acting against one another? Which direction is gravity? Which direction is my normal force? The sketch will give you all of this. It doesn't have to be beautiful artistically, but it does have to be accurate scientifically. The second point is, after you've done your diagram, is find your net force. That means along each coordinate axis you have to apply Newton's second law, F equals ma, by each component. After you've done this, you can apply some constraints. What's modifying the situation here? What will my equations look like? And then you can start to solve your system of equations. So you build your equations first from a sketch, then finding your forces, applying whatever values you have here, applying whatever constraints you have, solving the system of equations. Then you can substitute in. If you have a function, you can either integrate or differentiate to find what it is you need, and then you can apply initial conditions, VI or acceleration or whatever you have, to obtain the final answer to your question. I have to emphasize that most people usually don't like doing the free body diagram. They feel it might make them look ridiculous if they're just putting very basic arrows onto their diagram. But don't skip this step for any reason. This details all the forces involved in your system, and it tells you the directions of all the forces involved. And it's those directions that are truly important. Is a vector positive? Is it negative? Is it acting at an angle? This diagram will tell you all of these things, and really assists in understanding your problem. What trig functions do you need? What direction are you working in? So, taking a look at force calculations, let's look at the most simple case we can, which is a linear force in the x direction. Here we have a mass m subject to a force F, and you can see the red force vector acting on the mass here. If we apply our force, we'll get a corresponding displacement of our mass. Now, that would be a relatively simple free body diagram. We could also see a situation where we apply a positive force, Fx, but a negative force of negative Fx in the negative x direction is applied to this situation. If the acceleration in the negative direction is equal to the acceleration in the positive direction, then F equals ma for both sides of this system cancels. If you're just doing this by equations without drawing a diagram, you might simply add Fx to Fx and end up with 2Fx. by taking into account the directions, you can see that the fx's cancel and give you an overall f of 0. Now, situations in reality are never quite as simple as having all of our forces neatly aligned in the x direction or neatly aligned on the y-axis. Realistic problems often involve such cases as someone pulling an object at some angle. So here we have a person pulling a large undetermined block of something from the left to the right. Everything's in the positive x direction, but this force here, and in the positive y direction, this force here is actually a combination of an x force and a y force. Its components are in the x direction and in the y direction. This means this force F is not equal straight out to Fx, and this angle theta from the horizontal has to be considered if we're calculating the true force in the x direction versus the force F. And the same is true of the y direction, and you can probably tell we'll end up with trigonometric functions in the y and the x, usually sine theta in the y for this case and cos theta in the x, to calculate fx and fy respectively. So if we analyze that situation as a diagram, here's our mass being pulled with some force F. This force is applied at an angle theta, then the force in the x direction will end up being F cos theta, the projection of this force F on to the x axis. And this should be remembered in all calculations that you do. So let's take a look at an example, a somewhat odd but realistic example. Here's Oprah Winfrey, and Oprah wants to pull a wagon of meat. Don't ask why. Oprah wants to pull a wagon of meat that has a mass of 100 kilograms. She's applying a constant force of 135 newtons along the handle of this red cart at a 55-degree angle to the horizontal. So we have the mass of the meat. We're ignoring the mass of the cart. We'll assume that that's implied with the mass of the meat. And we have a theta of 55. First thing we want to do is draw a free body diagram for this system. So in this system we will have, of course, our normal force and our force due to gravity acting against one another. This means in the y direction these should cancel and we won't see any particular effect from these two. But in terms of our forces in the y direction, we don't just have the normal force, we also have the fact that Oprah is pulling upwards on this handle. So there will be a component of her force in the y direction. But if we ignore friction, so let's not worry about frictional forces or retarding forces acting on this cart, what's the total force acting on this wagon in the horizontal direction, in the x direction? So let's get our diagram back. We've got Fn, we've got Fg in the y. She's pulling with a force F that will have an x component to it. And here's what we have. Here's my scruffy diagram. This is all that your diagrams have to look like. I've got a force of friction on here, but we're ignoring that. All we care about is what's going on in the x direction in terms of this force. We know she's pulling with a force of 135 newtons, and she's doing it at a 55-degree angle with a mass of 100 kilograms. The forces in the y here will be 100 times 9.8, which will give us 980. We're just doing that for completeness. But the force in the x direction will be 135 newtons that Oprah is actually exposing the system to, that she's subjecting to the system. So her force is 135 times cos of 55, the angle to the horizontal, giving us 77 newtons. Having found the force, part B wants us to find the corresponding acceleration to that force. This should not be particularly difficult. We're now armed with our 77 newtons, our 55 degrees and our 100 kilograms, but we don't necessarily have to employ everything all over again. As we saw with the equations of motion, sometimes you can make your life easier by just thinking simple. And, as we saw, F was equal to ma, meaning A is equal to F over m. So to find our acceleration, we simply take our force in newtons, 77 newtons, and divide it by the mass in kilograms of 100, giving us 0.77 newtons. So that was a relatively simple problem. We'll take a look at some more complex problems as we move on, where we have to resolve the y and x directions. But I do want to mention one caveat to the rules we just discussed. In these previous examples, if we pulled this system with a force that had an x and a y component, to calculate the x component we found f cos theta. To calculate the y component we would use f sine theta. We would resolve this triangle here. Now, if we're to look at a system of an inclined plane, then we're taking a slope and putting our mass on a slope. If we put our mass on a slope, gravity will still be acting on this system. And this is a very important point, that gravity always acts straight downwards. Do not put your mass here and then put gravity coming out of the bottom of the mass like this. There is a component of force in this direction, but it is not mg. This blue line is not mg. This green line will be negative mg straight downwards. Your normal force, though, confusingly, will come out of the top of the mass still. If we place this object on this ramp, it will feel a force F down the ramp. The ramp is angled at an angle of theta. Now, one of the things we do to simplify this problem and make it solvable is look at our xy coordinate here. If we put the xy coordinate, such as x is this way and y is this way, as this block slides down the slope, we would have to keep track of this block both in its motion in the x coordinate and the y coordinate, making our life significantly more complicated. To avoid this, we can rotate our entire coordinate system and say that the positive x direction is down the slope. We're looking at this in the frame of reference of the mass. So x is down the slope, meaning this mass is not moving at all in the y direction, but is sliding down the slope in the x direction. Now, I'm going to add a little bit more complexity here and say what happens if we put a rope on this to hold it still. Well, if we put a rope here and we apply a tension and we're pulling this mass up this slope, we'll end up with a force that we're about to discuss soon here, which would be friction. And people are usually familiar with friction. Rub your hands together, your hands warm up. That's the interaction of the particles in your skin and the loss of energy from the motion you're putting in. So friction is acting down the slope here, T is acting up the slope, pulling the mass up the slope. Now the point I really want to make here is previously, when we looked at our x direction, F was equal to F cos theta, essentially. Fx was F cos theta. But on the slope, and this is very important, when you put your mass on a slope, you are no longer resolving the same horizontal triangle that you were in, say, the Oprah problem. You are resolving the forces in this triangle. And this vertical triangle means that mg cos theta is acting downwards from the block, and mg sine theta is acting in the x direction of the block. So if we're to detail all our forces, let's simplify it a bit. We would have mg cos theta coming out the bottom of our mass. We've got a tension, we've got a force. This is a much more realistic scenario than we've seen before. Our normal force, of course, is coming out the top of the block, mg always straight down. And you can help remember mg being down, where if you had a mass, like a small sphere or something, attached to this mass and let it dangle due to gravity, it would point straight down. mg cos theta is pointed this direction. This theta here is not an angle you need worry about. This theta is always equal to this theta. This theta is the angle you have rotated the plane through. So theta here is the same as theta here. And this is something that is usually provided, or the thing you want to find. But as I said, when we're looking at the components of force here, we always had f of x being cos theta, f of y being sine theta in the previous cases. In this case, when you put your mass on an incline, these switch, and cos theta is in the y direction and sine theta is in the x direction. Please remember this when solving problems. You can resolve this triangle every time you do this problem and prove that this is true, but this result is very important, and students frequently mix up their sine and cosine when they are given a system which is on a slope. So as we said before, when we talked about Newton's first law and introduced it, if you take an astronaut in the vacuum of space and he fires a thruster, he would have to provide an equal and opposite thrust in order to stop himself. If he didn't, he would just continue on and on and on. The thing that's missing in the vacuum of space is friction. The force that brings everything that is essentially moving within our atmosphere to a standstill. Even in space, like I said, there's 2 or 3 particles per cubic meter, and if he travels long enough for millions of years, after having run out of air and consumables, if he travels long enough, eventually those 2 or 3 particles per cubic meter will inflict a force on him and will stop him. But for our purposes, that's not a length of time we want to wait in terms of an experiment. The situation you will nearly always see is the first situation we discussed. Provide a ball with an initial force, and equal and opposite forces, such as surface friction and air resistance, again we'll assume air resistance is small, will bring our ball to a stop eventually. And this is our frictional force. If we're to look at our free body diagram, and by the way, it wouldn't matter if your force F was this side pointing this way or this was this side, as long as the directions are correct. Here we are providing a driving force to this block, moving it from the left to the right. If we do that, there will be an interaction here between the block and the surface. This will be surface friction, and will provide a resistant force opposite to the direction of our motion. Here we have mg downwards, we have n upwards, so in our y direction our forces should cancel, negative mg, positive mg. And in this direction, F and F. Now, for a stationary object, this force has to be smaller than this force. For the point where this force equals this force, the object is still stationary, but it's about to slip. As big red F there exceeds small little f, the object will start to move to the right, but it will have to continually overcome the force of friction. So where does this force of friction come from? Well, every object has chemical bonding. It has an actual molecular nature on its surface, and if you actually magnify this and you actually look at it very close up with high power magnification, what you'll see is each surface has these little peaks and troughs in it. It has undulations, and it's those peaks that are rubbing over one another as the materials move. And as they rub over one another, they experience a force which holds them back, and it's an inefficiency. Energy is expended by doing this. So that's why when you rub your hands together, you're essentially rubbing your rough skin from one hand on the other, and creating energy between them, losing energy from motion to heat. And this friction acts against the direction of your applied force. Now we're going to discuss two types of friction. The first one is static friction. In the case of static friction, this is the force that holds things still. Fs, force of static friction. So if we apply a driving force of F to this block, we have to apply a force F greater than Fs to start this block moving. Static friction is the score that F needs to beat to start this object on its motion. And the equation is relatively simple. Fs, the force of static friction, is equal to mu times n. Mu here is a constant, a coefficient of static friction, and this is a specific value, and this value is related to the chemical bonding in each of the objects that are interacting. So if you were pushing a piece of metal on a wooden plank, you would have a specific value of mu, which was for, say, steel on wood. If you were pulling a concrete block along a roadway, you would essentially have concrete versus asphalt. If you are scraping, say, a piece of glass over a piece of sandpaper, you would have another mu for glass sandpaper interactions. And usually in your calculations, you either find mu, or most often for typical objects that interact, and typical materials that interact on a frequent basis, like steel, aluminium, any of those or wood, any of those types of materials, mu is usually tabulated and available for you to use, or in a formula sheet that you'll be provided. N, though, is our normal force, m times g, the force that is opposite to the acceleration due to gravity. That means when our force Fs is equal to mu n, the block is on the verge of slipping. If our driving force, the big F, is bigger than small f, then that means the block moves. And this point where F is equal to F, when we are on the verge of making the block slip, is very important. And often a point we can calculate and say any value above this is a moving system. Now when your system does move, when you exceed Fs, your block starts to slide. When that block or object starts to slide, your regime of friction changes, and you go from Fs, a force of static friction, to what's referred to as a force of kinetic friction. And the force of kinetic friction is essentially exactly the same in its effect as Fs, it's just for moving objects. So you have Fs for stationary objects, you have Fk for objects which are moving. And again, the direction of Fk is always opposite to the direction of the applied force. And the formula is identical to that for static friction. Fk is equal to mu k times n. So you might be asking, Dr. Horn, you mercurial polymath, why are we doing two different formulae? The reason being, because mu k is a coefficient of kinetic friction. The coefficient of kinetic friction has a different value to the coefficient of static friction, meaning mu k for most natural materials is lower than mu s. So think about trying to move house or move furniture around. If you're trying to push a heavy desk or a heavy couch, it's often harder to get that motion started to get the object moving than it is to keep it moving. You don't want to stop because you know you're going to have to put in more work to get that object moving again. The reason being is because Fk is usually lower than Fs. The force required to keep something moving is often less than the force required to start it moving, because μk is often lower than μs. But even if you are pushing your object, you'll have to keep applying a force F to keep overcoming Fk. Fk still acts against your force of friction, your driving force, and will slow your block down. If you're driving a car on a flat level surface, you'll have to keep providing a force from the engine to push it forward. If you take your foot off the accelerator, the car will come to a rest. So in terms of friction, you have these two main equations. Fk equals μkn, Fs equals μsn. And those mu values are based on the bonding in the material that makes up the moving object and the surface it is running on. And typically these kind of coefficients are the things you'll see. Steel on steel is about 0.74, aluminium on glass 0.6, glass on glass 0.9, ice on ice 0.1, and you can kind of see here human joints have very low coefficients of friction. That being the reason that we tend to like to replace joints of older people. Younger people who will live longer will end up wearing out replacement joints that are made out of steel and composite materials because their forces of friction are so much higher, and they will then require an invasive operation to have those joints replaced again, whereas natural joints, which should be used for as long as possible, have much lower coefficients of friction. Something else to point out here is μk, as you can see, for all of these values is lower than μs. So the coefficient of kinetic friction for natural materials is less than the coefficient of static friction, meaning it's easier to keep something moving than it is to start it moving. There are materials out there where μk is bigger than μs, but these tend to be synthetic, and I will not delve into those. This means we can draw graphs of our driving forces versus our static frictional forces. And if we draw that graph, what we're seeing here are static and kinetic regions. This is frictional force, this is driving force on the x-axis. If we put force into our system, we are pushing and pushing and pushing our system and providing a driving force. Eventually, the driving force will exceed the frictional force. So here the object is not moving and our driving force is building up and up and up. Eventually that force will exceed frictional force at this point and the frictional force will drop. So here's a frictional force dropping down. This should have little undulations all the way through, just like this, as the force varies as those peaks and troughs in the material catch on one another. This means we can calculate our force of friction here from this graph. But this is an important relationship in that we're putting in force, providing a driving force, providing a driving force. As we overcome that force, the overall force of friction will drop and you'll end up with this characteristic graph. This point here, if you're looking at one of these graphs and trying to interpret it, is the point where our driving force exceeds our static frictional force. And that's important, because that means that the magnitude of Fs equals the magnitude of F. And that's the point you're nearly always trying to calculate. What's the force required to get something moving? And force generally acts in the opposite direction to Fs and Fk. Fk is nearly always less than Fs, and μs and μk are independent of any surface area, so don't worry about how much of the material is interacting in terms of area.